Hello, everyone. My name is Jericho Manalang, and I'm here with Ben Getz, Nathan Sianipar, Joseph Long, and today we'll be presenting our project, Bad Data in Control Flow Integrity. For this presentation, we'll start with the introduction, followed by the explanation of what control flow integrity is, what non-controlled data attack is, then we'll have a demo of that said attack, and we'll end with the mitigations and defenses for the attack. Here are some of the key concepts that we'll get into during our presentation. For the introduction, we'll have three things to talk about, which are the context, problem, and the motivation of these projects. For control flow integrity and non-control data attack, we'll talk about what they are and some attacks that are related to them. Then, as shown in the previous slide, we'll have a demo. And after a demo, we'll talk about the mitigations or defenses. Then we'll end with conclusion. And with that, let's get into our presentation. Imagine a scenario where attackers can no longer hijack a program's execution. Attacks like return-oriented programming or return to libc are fully mitigated. Thanks to Control Flow Integrity, or CFI, programs are now restricted to following only legitimate paths of execution. With that, it sounds like we've solved a major part of software security, but with a perfect control flow enforcement, that doesn't mean a program is completely secure. Just because attackers can change where the program goes doesn't mean they can't change what it does. As a context, well, control flow integrity has become a key defense in preventing control flow hijacking. It works by ensuring that execution only follows expected paths, like protecting return addresses, jump targets, and function pointers. Today, CFI is integrated into modern compilers, operating systems, and even embedded devices. It's a well-established defense and a necessary one. However, while CFI protects how a program executes, it doesn't really protect the data the program relies on. And that leaves a significant gap in overall security. And with that, we'll have problems. Many modern attacks don't rely on altering control flow. Instead, they focus on corrupting important data, what we refer to as a non-controlled data. For instance, imagine a program that checks whether a user is an admin using a simple flag. If an attacker changed that flag, perhaps through a buffer overflow, the program will follow the correct execution path. But now it mistakenly believes the attacker has admin privileges. Another example is consider a program that opens a file and displays its contents. If the file name variable is overwritten, the program could end up opening a file the attacker isn't authorized to access. Again, the control flow is unchanged, but the behavior is compromised. And here comes our motivation. These kinds of attacks, ones that don't violate control flow but still change a program's behavior, are what our project focuses on. We wanted to explore what's still possible for an attacker if we assume that CFI is perfectly enforced. In other words, if control flow hijacking is completely off the table, what other vulnerabilities remain that the attackers could use? And to answer that, we implemented an example of a non-controlled data attack. Our goal is to show that even under strong CFI protection or a perfect CFI protection, an attacker can still compromise this system by manipulating the right data at the right time. So, to better understand this, we'll first take a closer look at how CFI works, then we'll walk through a real non-controlled data attack we implemented, and then we'll discuss the defenses that might help address these gaps. With that, I'll pass it to Ben, who will start by explaining the fundamentals of control flow integrity. Thank you.
My name is Benjamin Getz, and I will now be talking about control flow integrity, or CFI, which is a key defense mechanism in modern security for programs. CFI is a security technique designed to ensure that a program executes and follows its intended path only and does not deviate from how it was programmed. It uses a pre-computed control flow graph, or CFG, to map out all of the valid paths the program is allowed to take. The goal of CFI is to prevent unauthorized changes to the control flow, such as attackers hijacking a return address or function pointer to alter how the program executes in real time. So by doing this, CFI blocks unintended jumps in the program's execution and inhibits classic exploits that rely on modifying the control data. So how does it actually work? There are three main steps in the process. First, building a control flow graph. Here, during compilation, static analysis is used to map out all of the transfers that the program is allowed to execute, such as calls, jumps, and returns. Next, within the code, the program is modified with runtime checks at each of these transfer points. So each call, jump, and return, a runtime check is implemented, and at these checkpoints, the code just makes sure it's executing properly on one of its known allowed paths. And finally, the runtime enforcement. During runtime, whenever the program makes an indirect jump or call, the checkpoints will check if the target is allowed to run this specific call or jump or return, and if not, the execution is blocked, and depending on the setup, an alert could be raised. So this system prevents attackers from being able to redirect within the program and avoid malicious code paths. So CFI was developed to combat a range of classic control flow hijacking attacks. So some of these include return address overwrites, return-oriented programming, and pointer hijacking. So return address overwrites is exactly how it sounds. It overwrites where the program will return to after executing a function, which the attackers use to jump to malicious code that they have written. Return-oriented programming is similar. However, attackers tend to chain multiple code snippets together that already exist within the program. So they are able to jump around between code snippets that already exist, so it becomes harder to detect. And they use these jumps to different code areas to perform a malicious action. Finally, pointer hijacking is another technique that attackers use where they overwrite a pointer to redirect the program flow. Again, somewhat similar to the other attacks, however, they're overwriting pointers to functions rather than return addresses after they come out of a function. But not all attacks target the control flow. So now I will move on to discuss non-control data attacks and how it affects security practices such as control flow integrity. So non-control data attacks manipulate memory without altering the control flow. So this makes them harder to detect, and they are often able to bypass protections like control flow integrity or data execution prevention. So for example, an attacker might be able to change a flag or a variable. So this doesn't affect how the program runs. It just affects some of the data that the program uses, which can cause malicious intent within the program. So now let's compare control attacks versus non-control attacks. Control data attacks target things like return addresses and function pointers with the goal of hijacking the program's execution. Non-control data attacks focus on logic within the application, such as changing flags, changing variable counters, loop counters, or altering login data to alter the program's behavior. Defenses like stack canaries, control flow integrity, etc., are effective against control data attacks. However, the non-control data attacks can often bypass these security measures, making them harder to detect. So here are some common non-control data attack techniques. First, flag tampering is often used to change Boolean variables. For example, if there's a flag set true or false to let you know if a user is an admin or if they've been verified, that sort of thing. The attacker will alter these variables to gain access to the program, impersonating, an admin or a user that has authority. Next, pointer redirection will redirect a data pointer to memory controlled by the attacker. So instead of with the control flow attacks where they redirect function pointers, here the attacker would redirect a variable pointer to point to data that the attacker can input. Field corruption is where the attacker would attempt to modify a structure's field, such as an array index or the size of an array, to alter the program's execution that way. And finally, session modification. That is where, the attacker aims to alter IDs or tokens stored in the memory that allow them to impersonate another user. So similar to how is admin in flag tampering could be set to true to impersonate an admin, here they would alter the password stored in memory to gain access that way instead. So now we'll look at some real-world examples. Here you can see a few of the different known non-control flow attacks. As you can see, they target data rather than altering program execution with things like data and password leaks or writing to protected files. These examples show how non-control data attacks can be just as devastating as traditional control flow hijacks, especially when they go undetected. So to wrap up this section, control flow integrity is a powerful and necessary defense for classic attacks. It limits the attacker's ability to hijack execution. However, as we've seen, non-control data attacks can be very dangerous as well, as they can often bypass these traditional defenses. So now we will move into a demo of a simple non-control flow attack.
Hey everyone, my name is Joseph Long and I'll be discussing the demo part of our project and presentation. In this demo, we showcase a non-control data attack, a form of memory corruption where we don't hijack control flow, but instead manipulate critical program variables like access flags. The program is written in C and is ran within the Windows subsystem environment for Linux. Our program is basically a one-factor authentication script that displays a file's content, which is hard-coded into our program. Now, before going into the program, I will first go over the compiler in order to run the program. Here, FNO Stack Protector, this will disable stack canaries, which is normally able to detect stack buffer overflows, which will be the basis of our demo. The Z execute stack, this makes the stack executable, allowing shellcode on the stack to run. The NoPy disables position independent executable, so addresses in memory are fixed. The -G includes a debug symbol. And -O, a program, basically just sets the output binary name to program. And a bad program v4 is our source file. So I'm going to go ahead and run our program here. I'm going to go enter in our username and enter in the correct password. As you can see here, since we entered in the correct password, we're able to view the file's contents, which is super secret information, as shown here. And now I'm going to go ahead and run the program again and enter in our username and the incorrect password. As you can see here, we don't have access to the file's contents and it's access denied. As you can see here, we don't have access to the file as it's not displayed to us on the console. Now I'm going to show an adversary or a hacker entering in a script into our program in order to view the file's content. As you can see here, this command crafts a specific input to exploit a buffer overflow vulnerability in the program by sending 68 letter A's to create a buffer and reaching the adjacent memory in the script. And next, we're going to overwrite the next 4 bytes with 1000. We're going to try to attempt to flip the flag. And then we're going to end it with a new line. Hence, this will be the non-control data attack. And you can see we are successful. We are able to see the file's contents without even entering a username nor a password. And now I'm going to go ahead and introduce our code. On line 4, this is where we define the admin key or the password. Line 6 through 9, this defines a user struct with a fixed size username buffer, and the isAdmin flag is used for control access. Line 11 stores 2 users, an admin and a guest. Lines 13 through 19 is our setup function for our users, and both of them will have the isAdmin flag set to 0. Moving on to the login function. Here on line 25, this is where the vulnerability occurs. The gets function has no bounds checking, and since we know that user 32 is followed by an isAdmin flag, if we attempt to do a buffer overflow on this memory location, then we are able to flip the flag from 0 to 1 here. And you can see on line 32 or 31, if the password inputted by the user is equal to the admin key, then we're able to set the flag to 1 in normal conditions. But when a hacker or adversary enters in a script that exploits a non-controlled data attack, they're able to view the contents of our file named secret.txt without even knowing the password itself. Now that we've run the program and checked out the code, let's go ahead and look into the memory. First, we're going to run the breakpoint at check admin. Next, we're going to insert the non-controlled data attack into our program. Next, we are going to the memory location. For the first line, you can see this is the beginning of the first user at index 0. which is a 32-byte character array. You can see it's completely filled with 0x41, which is the ASCII value for the capital A. And you can see the A's continue throughout all the lines. As you can see, the A's continue all the way through the next several lines, which is our attack input. Now, if we look down here, you can see it changes from 0x41 to 0x01. And this is where it gets interesting. These 4 bytes don't belong to the guest user buffer at all. And this is the memory location of the user.isAdmin flag. By overflowing the guest username field, we skipped over multiple variables and structs in memory and landed right on the admin's is flag, flipping it to 1, even though we never typed the correct passkey. This, in essence, is a non-control data attack. We didn't hijack the code execution or modify return addresses. We simply corrupted a data variable, and that's enough to gain admin access. That's it for our demo. I'm going to go ahead and hand it off to Nathan to discuss mitigations and defenses.
Now we will talk about mitigations and defenses. Before we go on, I would like to quickly describe the difference between a mitigation and a defense. A mitigation looks to reduce the impact or likelihood of an attack, but does not eliminate the actual underlying vulnerability. Think of it as like a safety net. A defense, on the other hand, looks to directly prevent or block the entire vulnerability. Thus, if a defense is properly inserted, the attacker will not be able to take advantage of that vulnerability at all. We will first talk about mitigations and defenses for the demo that you saw earlier. The first mitigation we will talk about here is to replace the gets function with a safer alternative. The gets function allows buffer overflows and is unsafe and depreciated. One safer alternative to this is the fgets function. The fgets function allows the user to specify a max number of characters, helping to prevent buffer overflows. The other mitigation technique here is input validation. Input validation can be used to ensure user input is correct and within an expected range, helping prevent malformed input or buffer overflow. We can change the code from before to check for a certain length and alphanumeric cases of characters, and if the input does not meet these requirements, we can then tell the program to exit with an error message. Now, the first defense technique we will talk about here is to perform memory-bound checks manually. Doing this would help by ensuring the program checks whether data is within the allocated memory before accessing it, helping to avoid buffer overflows. We could change the code to manually check that the index being accessed is within the bounds, and if it is not within the bounds, we can tell the program to exit. The other defense technique we can use here is canaries and struct padding. We can use this to help detect and prevent buffer overflows by identifying when an overflow has occurred by inserting a sort of canary value between important data structures. We can insert this canary value, and if an attacker overwrites the canary field or alters it, the program can then safely abort. We will now talk about general mitigation techniques. The first general mitigation technique are data integrity checks. By using cryptographic hashes, checksums, and redundancies, we can use these to help protect sensitive data. We can tell the program to check to see if a variable is corrupted, and we can tell if it's corrupted if the checksum does not match the original value. If this happens, then the program can safely assume that there was tampering and go from there. The next technique we will talk about is privilege separation. We can use this technique to divide the program into multiple components with different privileges and trust levels. Thus, even if the attacker is able to overflow the main component and break it, per se, they will not be able to access the high privilege service without the proper privileges, helping to limit the damage that the attacker is able to carry out. The final technique we will talk about is controlled data isolation. Along the same lines as the previous technique, the privilege separation technique, we can separate control data like function pointers, from non-control data, like variables or flags, in the memory. Thus, even if the attacker overflows the buffer, hypothetically, they should not be able to reach the control data or sensitive data, reducing the options of what the attacker could do if they manage to break in. Now we will talk about general defense techniques. The first technique we will talk about here is memory safety. Memory safety looks to prevent out-of-bounds memory accesses, which is a direct counter to the attack we had in this scenario. If the attacker is not able to carry out the buffer overflow attack, then they can't overwrite any sensitive data. Thus, the root issue is eliminated. The other defense technique we will talk about is data flow integrity. Data flow integrity helps ensure that data dependencies in a program are respected, and a variable is only modified by a specific, legitimate instruction. If an attacker looked to tamper with a variable, hypothetically, the data flow integrity check will be able to detect and then move to block it. However, this can be computationally expensive and is hard to retrofit into existing programs. So this is a largely research concept, although it is a promising technique. The last technique we will talk about here is taint tracking. Taint tracking looks to track where data comes from and how it is and or was used. Thus, if there was an untrusted input, it would help this untrusted input from being used in any sensitive operation by detecting it. And then we can move from there by maybe sort of like explicitly sanitizing it or checking it, and if needed, other techniques also. Unfortunately, taint tracking can be expensive to implement, so it is mostly used in research or specialized environments.